In the smart city, everything is connected. From public transportation, traffic, parking in vehicles, to energy, water resources, education, and buildings. The enablers in the form of devices and systems constitute an unprecedented security challenge, with attacks potentially having impact on our whole society. With an ever-increasing number of vulnerabilities, it is of significant importance that devices can be kept up-to-date and secure throughout their lifetime. This is the background of the research project SMARTY, Secure Software Update Deployment for the Smart City, conducted at Lund University. It is a collaboration between the Electrical and Information Technology Department and the Computer Science Department. It is supported by the Swedish Foundation for Strategic Research. Every day, new software weaknesses are discovered, new exploit code is developed, and new patches to the vulnerable software are produced. As many devices are based on the same open source software, or at least have much software in common, a vulnerability in a software package will likely affect a wide range of devices. With easy-to-use exploits, it is clear that both the number of vulnerable devices and the number of potential adversaries reach significant numbers. To mitigate attacks, the devices must be able to receive and apply updates to software or firmware. While vulnerabilities and software updates are at the core of the project, we also take a broader view of security in a smart city context. This project aims to contribute to increased security for the smart city, divided into 4 domains. These domains are vulnerability management, device management, networks, and applications. In vulnerability management, our goal is to better understand vulnerabilities, and in our case, in particular, software vulnerabilities. This includes both identifying new vulnerabilities, mapping them to the software that is used by an application or a project, and enabling an organization to efficiently work with them to update their software and devices. Here, we are using machine learning to leverage and understand the huge amount of available security data that can be found. Machine learning is also used to make better mappings between disclosed vulnerabilities and the affected software. A smart city environment can be seen as a massively distributed system with a large number of devices. Managing these devices and keeping them updated is a challenge, for example when there are requirements to keep systems live all the time and when they are used for edge computing. We cannot assume that all devices are available for being updated at all times. This requires support for gradual updates, which in turn requires support for managing several software versions at the same time. In the project, we investigate how the software can be structured into microservices, and we use a composition language to describe their communication. We are also developing a configuration language for both devices and components. This language can be used for version control and to identify which updates are needed for each component of the system. For network security, we have a primary focus on 2 emerging important technologies. The first is software-defined networking, or SDN, for improving both security management and deployment of devices and services in the smart city. We consider both the security of the actual SDN deployment as well as SDN applications in the smart city context. The second emerging technology is the use of blockchains, and here we investigate how blockchains can be used in a public key infrastructure, or PKI. The integrity and unforgeability properties of the blockchain aligns well with the requirements for a PKI. Also, the decentralized nature of the data stored on the blockchain permits a robust implementation of a PKI. While the smart city relies on the technology to function, it is the applications running on top of this technology that makes it useful. A part of the project is thus devoted to proposing new applications and to support the security of existing ones. An example application is the control of traffic lights for emergency vehicles. Since the SDN has a global view of the network, it is possible to improve the overall efficiency of the traffic if we allow the SDN to control the traffic lights. Another line of research is the use of homomorphic encryption schemes in order to preserve privacy for applications. Being able to do computations on encrypted data allows for outsourcing of storage, and we can also support several entities doing computations on the same data without revealing their respective input. Securing the smart city presents a large number of challenges that need to be addressed. This project considers some of these challenges with the goal of spawning new ideas and evaluating others. Together with other researchers and projects, we hope to contribute to a higher security and privacy when we as a society slowly embraces the vision of the smart, sustainable city.